Section 4.1 problems. The first problem that models the amount of dollars spent at the shopping mall after X hours of shopping we did back in the PowerPoint slide. So let's do a variation of this. So we'll do a new number 1. New problem 1. Let's take a function, let's say f of x, that is 67.3 times 0.91 to the power x. Let's make that where f of x is the stock price in dollars, and we'll designate x to be number of hours after trading begins. So we're looking at the price of a stock at the beginning of the day, and the market opens, and throughout the day that price will fluctuate, and the price of that stock is given by this exponential function f of x, where f of x is that stock price in dollars and x measures the number of hours that have gone by during that one trading day. And we'll ask the question, we can ask two questions. A, what is price of stock at start of the day? What was the opening price of the stock when the bell rang? Okay, since x measures the number of hours after trading begins, this would be where x is equal to 0. If x is equal to 0, then f of 0 would be the price of that stock, 67.3 times 0.91 to the power 0. A non-zero number to the power 0 is 1, so this is 67.3 times 1. So the original price of the stock when the trading began was $67.30. Okay. Now, what happens to that price of the stock as the day continues? So let's ask in B, what's the value 5 hours later? So what is value after 5 hours? Okay, so x then is 5, number of hours since the trading has begun, and f of 5 is the value of that stock in dollars, 67.3 times 0.91 to the power 5. So exponents first, take 0.91 raised to the power 5, second multiply by 67.3, and we'll find that that's almost exactly $42. I mentioned the order of operations because if you multiply these two numbers together first and then raise to the power, you will not get 42. What you'll have there is the incorrect answer. So there's a variation of problem number 1. Problem number 2, graph the exponential function 3 to the x. We did that on the PowerPoint slides as well. So let's take a look at a variation of problem number 2. Instead of graphing 3 to the x, let's do a new number 2, and let's make let's make the function 3 to the power negative x, and take a look at that. So let's graph this. So what I'll do is I'll set up a table here, x and f of x, xy table, and we typically evaluate for values of x that are negative, 0, and a few positive values. And the more the merrier, but the numbers get out of control very quickly and very difficult to plot on a coordinate system. Okay, so when x is negative 2, f of negative 2 is 3 to the negative, that negative there I just wrote is this one here in the original, and then the value of x is negative 2. That makes the exponent positive, and it gives us a 9. At negative 1, f of negative 1 is 3 to the minus negative 1, or 3 to the first power, or 3. you can see right away that this function is starting to decrease. Yes, and it's not decreasing because the b value here is between 0 and 1. It's decreasing because the x value is negative, and I can comment on that as soon as we're done. I understand that as a point of confusion. At 0, 3 to the negative 0 is 3 to the 0 or 1, so 0 gives 1. And at 1, f of 1 is 3 to the first power, or 3 to the negative 1, or 1 over 3, so that now makes a fraction, it reciprocates it, so that's 1/3. And then at 2, the y coordinate at 2 is 3 to the negative 2, that's 1 over 3 squared, or 1/9. 1/9. Okay, if we transfer those to coordinate system, y-axis there, x-axis there, okay. The y-intercept here is 0, 1. So let's put 1 way up here. 0, 1. Notice when x is negative 1 and x is negative 2, the values are quite large, 9 and 3. And based on my scale, well, that's going to be very difficult to show on that particular scale. Points are very far up here at negative 2 and very far up here at negative 1. Why make this such a large gap? Because now we have to also accommodate these fractional values. That's why I say that these values, although they're very small for x, the numbers start to get out of control and it's difficult to scale, but the general shape of this will be exactly as described in a PowerPoint slide. When x is now 1, we only have 1/3, which is very small, and when x is 2, we have 1/9, which is right here. And the function is a decreasing exponential, like this, and gets smaller and smaller and smaller and smaller, but never gets to 0. So that's the typical shape. Now, why you say is that the shape? Because isn't this a b to the x where b is a fraction between 0 and 1? Well, yes, it is. Now, our function, here's where I'll explain this, our function is 3 to the power negative x. By rule of exponents, this means 1 divided by 3 to the power x. Okay, well, this is the same thing as 1/3 all raised to the power x. The reason why is a number raised to an exponent, here it's a fraction, the top gets raised to the power, well, 1 to the x is just 1, and the bottom gets raised to that exponent. So there you go. The original function, f of x, which is 3 to the negative x, that is exactly the same thing as 1/3 to the power x. And now we do have a b to the x where b is between 0 and 1. And that is the reason why this exponential function is decreasing, as shown in the PowerPoint slide. Let's go on to problem number 3. Use the graph of y equals 3 to the x to obtain the graph of a new function, 3 to the power x minus 1. Okay. This is an example of a graph transformation. The function g of x is the same thing as the function f of x, except x is replaced by x minus 1. So f of x minus 1 means go to the function called f, replace the variable x by x minus 1, and when you do that, you'll have the function g. This represents a horizontal, it's a horizontal slide. And it's a little tricky because it is to the right. And you would think that a negative 1 there would be to the left, but it is in the opposite direction. It's difficult in practice to take a graph and slide it, especially an exponential, because it looks almost identical to the original, but it's not. So the way I suggest that we do this is first consider the function f of x, which is 3 to the x, and we'll make a table of values, x and 3 to the x. Okay, now we already have these table of values, so I'll do this very quickly. Negative 2 is 1/9, negative 1 is 1/3, 0 is 1, 1 is 3, and 2 is 9. Okay. Now, to get the function f of x minus 1, which is our g of x function, you have to subtract 1 from each x coordinate. So we're going to subtract 1 from each x coordinate. And that will give us the values on the g function. So we'll do that, and we'll have x with 3 to the x minus 1 power. This is our g of x function. So if we subtract 1 from negative 2, we have negative 3. Horizontal slide to the right. I'm going to add, whoops, that's a big mistake. This is a to the right, so we are going to add 1 from each x coordinate because this is a slide to the right. I made the rookie mistake of seeing the minus sign and saying subtract. So if we add 1, negative 2 plus 1 becomes negative 1. Negative 1 will be 1/9. And now adding 1 will be 0, that will give 1/3. Adding 1 will give us the point 1, 1. Adding 1 here will give us 2, 3. And adding 1 here will give us 3, 9. Now you can check to see that this actually makes some sense because we know our function is 3 to the x minus 1. Let's check it here. If x is 3, 3 minus 1 is 2, and 3 to the second power is indeed 9. So it is consistent. Okay, now simply plot these points. And you'll obtain the graph of the g of x function. Now, when you do that, it's difficult to show. Here is our 3 to the x function, which goes through 0, 1. Our g of x function is slightly different. It's a horizontal slide to the right, which means that we take every point that's on the graph here of f of x, and we have to slide it over to the right by 1 unit. Every point gets moved over 1 unit, and then you get the graph of g of x. So it looks something like this. And there's 3 to the x minus 1. And this point right here, 0, 1, 0, 1 moved to 1, 1. So this right here is now the ordered pair 1, 1. And yes, we slid it to the right, but it often looks as though we moved it down. Moving an exponential down and sliding it left or right looks very much similar. So the more precise way to do this is the way I have here. Make a table of values, apply your transformation by adding or subtracting to your values of x, and then replot those points. Okay, let's take a look at the next example. Use the graph of 2 to the power x to obtain the graph of 2 to the power x plus 1. Okay, so we know in practice how to do that, but this is slightly different than the previous example. Here, f of x is 2 to the power x. G of x, you have to look at this carefully, is 2 to the power x, then plus 1. It is not 2 to the x plus 1. That is very different. Very different. So this is not what we have. This is what we have. Okay, what effect does adding a constant do to it? This is what's called a vertical lift, sometimes it is called, or it's a vertical translation. If it's vertical, that means we have to add 1 to each y coordinate on graph of f of x. So this is truly a vertical rise. So we look at the graph of 2 to the x. We could make ordered pairs, yes, and then we'd add 1 to every single y coordinate. Same value of x. We use the same values of x, but the y coordinate will be 1 more. For instance, when x is 1, 2 to the 1 is 2. When x is 1 here, we get 2 to the 1 is 2, but plus 1 more, and so now we get 3. So it lifts up the y coordinate by 1. Now when you try to show what this looks like on the coordinate system, here is the graph of 2 to the x. And of course that goes through 0, 1 on the y-axis. Okay. And we have to lift that up. So every point that's on the graph of 2 to the x goes up, vertically up, by 1 unit, because we are adding 1 to the y coordinate, and we will then get the graph of here 2 to the power x plus 1. And yeah, you know we lifted it up, but if you slide it, it almost looks the same as if you lifted it. So it is a bit tricky. So the idea of the graph transformation certainly applies. If you want it to be accurate, plot points. Take the points on 2 to the x, and for the very same x coordinates, add 1 to each y coordinate, and you'll get the graph of our new function here, 2 to the x plus 1. Let's go on to the next problem. This is the population of gray wolves, and we looked at the solution of this in the PowerPoint slide. So let's do a slightly different problem 5. So do new, number 5. Let's say population of a town, and let's name this to be P of t. P for population, T for time. So P of t is the population, and then T is number of years, let's say since 1995. So we'll measure time from 1995 forward, and P of t will be the population. And let's give you what that exponential function looks like. P of t will be 25,000 e to the point 023 t. 0.023 t. So this is a continuous exponential model, and often the reason why is that populations, well, at any given instant, humans are being born and humans die, and so that is a continual change in the population. The e exponential models continuous change, continuous growth, continuous decrease. So often with populations, or even money, the e exponential function is used. So we can ask for, let's say, 2 questions. Find A, the population of the town in 1995, and then B, let's ask the question, population in 2015. Population in 2015. Okay. In 1995, that represents the time at which the model begins to work. T measures the number of years since 1995. So 1995 means T is equal to 0. So we'll find the population at time 0. So that will be 25,000 e 0.023 times 0. Okay. Well, 0.023 times 0 is 0. E to the power 0 is 1. And 1 times 25,000 will give you 25,000. So the initial population is what it's often called. It's 25,000 people back in 1995. And then things begin to change from that point forward. Let's calculate the population in 2015. Okay, but 2015 would be how many years have elapsed since 1995. So that would be 20 years. So we'll find P of 20 in the same way. 25,000 e to the power 0.023 times 20. Be sure that if you're using the calculator that all of this is in the exponent. It's best to block it off like that on the calculator so that you are sure. Otherwise, the calculator will raise e to the power 0.23 and then multiply by 20. That's not what you want. You want the 0.23 times 20, which you could do first, and then raise e to that power. Lastly, multiply by 25,000. So when you do that, we should get approximately 39,601 people. So you see that the population is growing. In fact, I'll tell you that the population is growing by 2.3% because e to the RT, R is the decimal of the percent rate of change. No, rate of change, in this particular problem, it's growth. So we have R is 0.023, which means 2.3%. So the population is growing by 2.3%, and that's why it's increasing from 25,000 to 39,601. You would wonder then what would make the population decrease, and I'll tell you that that would be if the R value here is negative. If you have a negative value here for the R, then the rate of change will be decrease, and the population will be going down. Okay, what do we have? Problem 6. Problems 6 and 7 are the same as on the PowerPoint slide. So let's do a similar but different problem. So we'll do a new number 6 here. And let's take $10,000 to invest. This is P. And we'll get 3.75% interest. Okay, that's not R. R is the decimal form. So R is 0.0375. Always convert it to decimal form before using compound interest formula. And let's see, let's let T be 15 years. So let's invest for 15 years. So that tells us that T will be 15. And let's subject to monthly compounding. Monthly compounding. So that'll tell us the value of N is 12, since there are 12 months in 1 year. So let's get our compound interest formula here. A is equal to P times 1 plus R divided by N raised to the power N times T. So there's our compound interest formula. Let's substitute that in. We're investing $10,000 at the start. 1 plus R, 0.0375 is R, divided by n, which is 12, raised to the power n times t. So off to the side here, n is 12, and t is 15, and 12 times 15 is equal to 180. So the exponent is 180. It's often easier to do the exponent, especially when it's easy to do, off to the side. Now, I suggest evaluating this first, raising that to the power of 180, and then multiplying finally by 10,000, and you will find approximately that will have 17,535. Approximately that amount of money we will have after time of 15 years. Notice, as I said in the PowerPoint slide, if you start with 10,000 and you're ending with 17,535, that the difference between the two is interest earned. That's not bad, $7,535 for allowing the bank to use your money for a 15-year time period. Okay, let's take a look at number 7. Number 7 is the continuous compounding version of problem 6, so I will take our problem 6 here and do a version of that for our new number 7. Let's take the same problem, same numbers. So this is problem 6 with, let's do continuous compounding. Continuous compounding. Okay, so let's get our formula since we have all the values already known. P times E to the power R times T. Okay, and what will be the amount after our time period? We're still investing the original $10,000. That isn't changing. E represents the continuous compounding. R, 0.0375. T is 15. So here I'm putting that right in the exponential function because it's not an easy calculation as before when we did 12 times 15. Okay, very carefully block that off. Take e raised to that power and multiply by 10,000, and we will have approximately $17,550 after our 15-year time period. Notice that we earned a little bit more, but not a huge amount more, just a little bit more. But again, the more you start with, the greater the interest rate and the greater the time, the bigger the difference between the two. But it won't be a difference that will be fantastically impressive. It will make a difference. That concludes the problems for section 4.1.